Hey, in this tutorial we're going to be adding some basic 2D lighting. Now this 2D lighting that we're actually going to be creating is really kind of hacky and really simple. It's not true lighting, it's not Phong shading or anything like that. I wanted to keep the lighting implementation really simple for this series so that we can actually do all the complex lighting stuff like shadow mapping and Phong shading and all the specular shading and all that in the actual 3D series where it's more likely to be used. Because really for 2D the hacky little lights are typically all you need, and if you want to do something like 2D shadow mapping, there's plenty of resources online. I don't have to go step by step and teach you that. I'd rather move on to other things. So let's get started. The first thing we want to do is create our simple light class. Now this class is going to be another really simple implementation. It's just going to be a header implementation, so we just need a header file. We'll call it light.h, and I'm going to make it a part of Ninja Platformer, not a part of Bingen, because it's our little hacky light. And we're going to do pragma once, and we'll say class light, and everything is going to be public because there's no real reason to have getters and setters. We want to be able to do a get and a set on every member variable, so we might as well just make them public. Now what's it going to need? It's going to need a color, so we'll say bingen color RGB8 color. We need a position, so we'll do glm vec2 position, and then we need dimensions, so we'll say we'll just make it so that all these lights are spherical for now. We'll just say float size. Here we go, and we got to do some includes as always. Include glm.hpp, and include bingen vertex.h, I believe is where color is. Still to this day it's in vertex. It should be moved, but it hasn't been. Alright, so now we have the light. Let's go ahead and do a draw function as well, might as well, because that's what this is for, void draw. And it's going to take a bingen sprite batch and sprite batch. There we go, and we need to include sprite batch for that as well. And bingen sprite batch.h. There we go, and to actually do the sprite batch drawing, I'm just going to steal a little bit of code from box draw because it's pretty much going to be the same. I'm just going to grab this whole thing, and we'll go into, where is it, light.h, and paste it there. Now the difference is, instead of body.getPosition, we're just going to use position, so we'll paste that. Instead of dimensions, it's going to be just size, and we have the same size in the x and y. Now the rest of this stuff, the texture ID, we're not going to have a texture. We're going to be doing it in a shader, and I'll show you exactly what we're going to be doing here in a second. Let's just put 0 for that. For color, we're going to put color. For angle, we're just going to say 0 since these are circular lights. Angle doesn't matter. And for UV rect, now this is the one that's going to be a little bit weird. Not really that weird, but I'll explain to you exactly what we're doing here. What we want to do, let me undo all this stuff I was playing around with. What we want to do is we want to be able to render lights, but we're going to be doing it really simply. In 2D, we can do this really simple light rendering using just basic alpha blending. What we do is we just draw a quad that has the light boundary in it, and we just render this quad over everything with alpha blending. And we use a little bit of math in a shader, really simple math, to just kind of brighten the center and make it gradually get darker until at the edge it's completely transparent. And then we can give it color, we can give it size, intensity, all that, and we can just overlay that over all of our objects. If we draw this last, then we get basically a lighting effect that lights every object in the scene. Now, I'm not going to teach you shadowing or anything like that, like I said, and this lighting is very basic. It's not actual lighting, it's sort of like a fake lighting effect, but it'll work really well for our needs, and it's incredibly fast because we can just use sprite batch to render it. Now for the UV rectangle, what we're going to be doing is we're going to be passing in glm vec4, and we're going to pass in, for the x and y starting position, we're going to pass -1, -1, and for the dimensions, we're going to pass 2, 2. And let's be correct and say 0.0f for all of these since they are indeed floats. Now why am I doing this? Well, and I close paint of course. The reason I'm doing this is because what we want to do is, here we go, we want to have a box where we have -1 in the x, -1 in the x, and +1 in the y here, then 1, 1, 1, -1, and what is this, -1, -1. We want this because this is going to allow us to compute a distance. Because of this center point right here is at 0, 0. Thanks to our UVs here. And what we can do is we can compute the distance of every single pixel from the center. When the distance is equal to 1, we say that's going to be 0 alpha. When the distance is equal to 0, we're going to say that's going to be 1 alpha. And that'll give us just kind of a smooth fade from the center outward of just a little point light that'll look fairly well. And we're going to do linear. Linear isn't the best. You could also do some like squared stuff or cubic stuff. We'll experiment with that and see what looks the best. But we'll start with linear. Okay, so we have sprite batch draw passing in that. That's good. Now we need to just create a shader that'll render this. So let's go into our gameplay screen.h and we're going to make a new shader. We're going to grab, let's see, here we go. Texture program is going to be copied and we're going to call it light program. And then we build the shaders in onEntry, so let's go there. So compile our texture shader and then compile our light shader. I'm just going to grab all this and we're going to say, instead of mTexture program, we're going to say mLight program. And we're going to paste this for all of these. Now we're going to pass in the same attributes because we're using sprite batch, and you always need to use these 3 attributes for sprite batch. But for the path, instead of texture shading, we're going to make a light shading.vert and a light shading.frag. So, whoops, accidentally clicked Internet Explorer. Let's click on our little file explorer and bring up Ninja Platformer shaders. And I'm going to take texture shading and just copy paste it. And then I'm going to rename it to light shading, so we don't have to start from scratch here. And let's edit it. Alright. So here we have light shading.frag and light shading.vert. Everything here is pretty much the same except for fragment UV. We're not going to be flipping the Y coordinate or anything like that. We could, but it doesn't really matter anymore since we're just rendering a circle. So we're just going to say fragment UV equals vertex UV. And the fragment shader, we've got all these comments in here that don't make any sense. These are from way back when we were learning about shaders, and they still make crazy colors. We aren't even making crazy colors. We'll get rid of all that. We no longer are going to need a texture, so we're going to get rid of my sampler completely. We're going to get rid of this texture color right here. Don't need it at all. And what we're going to do is we're going to compute the distance. So what we need to do is we need to have a float distance, and this is going to be equal to, and the way we get the distance from any pixel from the center is we take the pixel's UV coordinates, say we're here, and we call the length function on it, and that will get us the length of the vector of that pixel. So say we're right here at 1 in the x and 0 in the y, we're going to call length on it, which is the same as GLM length, and it's going to give us a length of 1, and that'll be our distance. Then we just subtract that from 1 to invert it. That way we get 0 here and 1 in the center. So we're going to say distance equals length of fragment UV. And now what we can do is we can say color equals, let's make a vec4. We're always going to use full RGB, so we're just going to say fragment color.rgb. Then we're going to put a comma, and for the alpha, this is what we're going to change based on distance. We want it to blend based on distance. So color.a, we're going to multiply that by 1.0 minus distance. And this is going to give us the effect that we want. Yeah, let's get rid of that. Now, I'm not using texture anymore. However, we are using sprite batch, which thinks that we're going to be using textures. However, it doesn't matter. If we go into, let's see, Bingen and then sprite batch here. If we go to where it actually renders, here we go, render batch, it's not explicitly asking for any texture stuff. All it's doing is binding the textures. If we don't use the textures, it's fine. Nothing bad happens. If you remember, when we go to gameplay screen, into the draw function, here's where we actually set that uniform for the texture. The texture uniform gets set outside. So all we got to do is not set this uniform. And even if we did, nothing bad would happen. It would just silently not work. It wouldn't even give us an error. So we're fine here. Now let's go ahead and create ourselves a light. I'll make a light that is centered on the camera, and we can also make a light that is centered on the player. Now what we should probably do is have like a vector of light somewhere and then render all of those lights. But I'm just going to hard code this because being a little bit lazy, and I just want to show you guys how it works. It's not particularly important that we get it perfectly right the first time. So render some test lights. So we're going to say light, this will be player light, and we're going to reconstruct these every frame, but that's not really a big deal because they're so lightweight. It's just a couple bytes or a couple variables. So of course we need to include light. Include light. There we go. So the player light is going to be centered on the player. Let's say player light dot color equals Benjin color RGBA8. We'll make this super bright. The brightness is pretty much going to be determined by this last parameter, the brightness of the light. If we say 255, it's going to be really bright because at the center it's going to be not transparent at all. It's going to pretty much cover everything. Now we can say player light dot position, and what we're going to do for this is we're going to say equals mPlayer dot get position, and it looks like we don't have a get position. We should probably make one. Let's do that. Let's go to player. Let's make a get position. We'll say glm vec2 get position const and glm vec2 return value. We're going to say return value dot x equals m body. Is that what it is? Or m capsule dot get body dot get position dot x, and rv dot y is the y version. So we just change these to y, and then we just return rv. There we go. Now we can get the position in our gameplay screen. So light position equals player dot get position. There we go. And player light dot size. Let's go ahead and set this to 10. That'll be 10 meters across, or the radius will be 10 meters. I believe. No, it will be 10 meters across. Now we need to draw the light. So we need to bind our program. We're going to say m light program dot bind or use, and m light program dot unuse. And we need to send to the camera matrix, so we can just grab these two lines here and reuse them. And we'll do that right here. We don't need to define p uniform again, it's already been defined. And now we need to do the actual sprite batch stuff. So we're going to have a m sprite batch dot begin and an end and a render batch, and then in here we're going to render the light. So we're going to say player light dot draw, and we'll pass in m sprite batch. Alright, so let's just see what it looks like with the player light only right now. It's going to be really bright because our last parameter here is set to 255. And it looks like we have some shader errors. So fragme color is not defined. I definitely spelled that wrong. Fragme color should be fragment color. Where is fragme color? Here it is, fragme color.a. There we go. Save that, run it again, see if we get any more. There we go, and there you have it. This is our fake light, and it's really, really bright at the center. It has a value of 255 at the center, actually. Let's go ahead and add a light also that follows the mouse, and let's make the light for the player just a little bit darker. So let's change this to 128, and then for the mouse one, we're going to make another light. We'll say light, mouse light, and of course you're not going to want to, in your game, hand make all of your lights like this. You're going to want to have a vector, maybe even define them in files, but like I said, this is just for showing how it works. We'll say mouse light, what am I doing? Mouse light dot color. Let's make this equal to, we'll say the last will be 255. Let's make it like a magenta, something really ugly. For position, position's going to be a little harder, but luckily we have a function that we can use. We'll say glm vec2 mouse pos equals, and we have this mCamera dot get, or what is it, convert screen to world. We can convert a screen position to a world position, and thanks to our input manager we know the coordinates of the mouse because we can say mGame arrow input manager dot get mouse chords. It's a good thing we created all this stuff already, and now we can set the position. We can just say mouse light dot position equals this. Position equals that. And for the size, mouse light dot size, let's make it a little bit bigger. We'll say it's 15.0f. And since it's a little bit bigger, we can make it a little bit brighter maybe. We can say like 150. Let's see what this looks like. Oh, and I didn't render it because we aren't looping through a vector. It's not going to automatically add itself. So we're going to call mouse light dot draw with m sprite batch. Don't hard code this. Alright, now we run it. And there, now we have a little purple light that follows the mouse, and it will blend over the player with alpha blending. But there's actually other kinds of blending we can do too. Right now we're using just the basic alpha blend, which is, let's see, it's GL1 minus source alpha and GL alpha, or GL source alpha. Let's see. Let's do Control F for GL blend func to see where we are setting it. I guess it's just using the default. GL blend, where are we? Here we go. In window.cpp we're setting GL enable GL blend, that's of course what we want, and then we're setting GL blend func, GL source alpha, GL1 minus source alpha, and this is just the standard blending, the standard alpha blending. Let's see what it looks like with something else, a different alpha blending. We can try additive blending. So let's go to gameplay screen, and let's come down here. First, let's make sure we always reset it, and we can do that after we render it. So down here at the bottom, we'll reset the blend func, reset to regular alpha blending. And now let's do some additive blending. Additive blending. Now the way this works is the first parameter here, this is the source factor. So what we do is we say source alpha, meaning say source alpha is 1, it's going to multiply the source color by 1. And this is the destination factor. Here we have 1 minus source alpha. So if source alpha is 1, this is going to be 0, and we're going to multiply the destination the destination color by 0. So you get full color from the source and no color from the destination whenever alpha equals 1.0. However, if we say GL1 and GL1, now this is additive blending. What this is going to do is it's going to take, and really it shouldn't be GL1, it should be GL source alpha and GL1. What this is going to do, it's going to say, same as before, just take the alpha and multiply it by our color. However, for the destination color, instead of multiplying it by 1 minus source alpha, we're just going to multiply it by 1, meaning the destination alpha is always going to stay the same. Now if we run it, we're going to get something a little different. It's going to blend a little bit better, but we've got compile error because I forgot a semicolon down there. Now let's run it. Oh wait, I didn't even put that in the right place. What am I doing? This is in the initialization. It needs to be in the draw. We need to move this down to where we draw the lights. So additive blending there, and then reset to regular alpha blending down here. Don't know what I was thinking there. And now we run it. And this will give us additive blending. And things are going to be a lot brighter with this. As you can see, the player is a lot brighter and it looks a lot more natural because it's adding to his color. It's not taking away his color at all. And then if I move the purple light over, it gets even brighter because all of the different colors are getting added together and really kind of washing it out. Now we would probably want to make the objects around the scene a lot darker naturally, so maybe their base color should be a little bit darker than it is. You guys can mess around with that pretty easily. And we could also experiment with some different formulas for the actual lighting, because right now our linear lighting model is pretty unrealistic. Now one formula I've experimented with and I think looks pretty good is this one. If you go to Wolfram Alpha, you can type in formulas and have it graph it for you. I'm graphing 0.01 to the x minus 0.01 from 0 to 1. And this will be the curve that we use for our lighting, which it's a little bit more realistic. It drops off quicker and then kind of slows down. It's a much smoother curve. Whereas originally we were using this, we were just using 1.0 minus x from 0 to 1, which looks a little bit like this, just a straight line that doesn't look very good at all. So let's try that and see what it looks like. Instead of 1.0 minus distance, we're changing the formula to pow for the power, and we're going to do 0.01 to the distance. And what did I say? I said minus 0.01. And there we go. So now let's see what this looks like. It's going to make our lights a little bit darker, so we'll want to increase the size if we want them to stay roughly the same size. There you go. This is the new one. It looks a lot more natural. They're a little bit smaller, so let's make them bigger. Let's say that the player light is going to be 30. We'll make it 3 times bigger. And we'll do same thing for the mouse light. We'll set it to 45. And there we go. Now it's much bigger, and the shape is just a lot more natural. It just feels better. Now you can use a different formula if you want. You can experiment with whatever you want. Now my exercise for you is to try to figure out how to do point lights or sorry, not point lights, spotlights. For spotlights, you'll want to be taking into account rotation, of course, and the math you're going to use, just as a hint, is going to involve the dot product, most likely, so that you can get the angle from the horizon or wherever you're looking at, and each pixel in your little texture thing. So thanks for watching, guys, and I will see you in the next tutorial.